In the last video, we were looking at intermolecular forces, and specifically London dispersion forces, which are weak intermolecular forces that result from a temporary dipole, a temporary unequal distribution of electrons, which causes a partial positive and partial negative. But if that partial positive and partial negative is temporary, the attractive forces between those molecules is pretty weak. Dipole forces involve polar molecules. Blast from the past. Now here it's called a dipole force, but honestly I just call it a dipole force. Polar molecules are molecules that always have a partial positive and a partial negative end. This is a permanent dipole. So a good example, like HCl. If I draw the Lewis structure, hydrogen and chlorine. 2, 3, 4, 5, 6, 7. Zoop. Okay, so here's my Lewis structure. And now let's say I look at the periodic table. And I'm just kind of eyeballing chlorine and hydrogen. Chlorine has 7 valence electrons. And I mean, it's a relatively small atom. I mean, they're both kind of small atoms. But chlorine definitely has a higher electronegativity, which means that the electrons in this bond are always drawn closer to chlorine, because chlorine has a higher electronegativity, which means that this is always a polar bond. So this molecule will always have a partial negative chlorine end and a partial negative hydrogen end. If the electrons are always drawn toward chlorine, electrons are negative, so chlorine would have the partial negative. This is a permanent dipole. This molecule is polar for life because the electronegativity of hydrogen and chlorine is always so different. Okay, so that's why these dipole forces are a little bit stronger intermolecular force. It's the same general concept as the London dispersion force, but it's a permanent dipole, not a temporary dipole. So let's say this is like your chlorine, and this is your hydrogen. Chlorine, hydrogen. Every time you have a partial positive chlorine, it will always be attracted to the partial negative, did I say partial positive chlorine? I said partial positive hydrogen. It will always be attracted to the partial negative chlorine of a neighboring molecule. This attraction is permanent for life. This attractive force between the molecules is your dipole force. It makes sense, right? Opposites attract. So if you have a molecule that's got a partial positive end, it'll be attracted to a partial negative end on a neighboring molecule. If I do a phase change, it's this intermolecular dipole force that I need to overcome. I want to separate the HCl molecules, but I do not want to break the HCl bond. If I break this bond, now that's a chemical change. But if I just break this intermolecular force, I still have HCl molecules. They're just separated. So maybe instead of the liquid phase, now they're in the gas phase. So these dipole forces are a little bit stronger intermolecular force, resulting from attraction between permanently polar molecules. The partial positive is always attracted to the partial negative. Okay, cool. These are very, very common. And they're very much related to something called a hydrogen bond. Hydrogen bonds, these are good. They're even stronger intermolecular forces. These are good. Now, obviously, there must be hydrogen in the molecules. They're called hydrogen bonds, right? They're just kind of an extreme dipole force. Dipole forces and hydrogen bonds are very, very much related to each other. The same concept. We're going to have polar molecules, where one end is partial positive, one end is partial negative. The opposite ends of the molecules are attracted to each other. We have to have hydrogen, and it has to be bonded to FO or M. Fluorine, oxygen, or nitrogen. So here's how I remember it. I always say hydrogen bonding is fun. Well, it is fun. FON. They are the three most electronegative elements on the entire periodic table. They're small atoms, which means lots of attractive forces, and they really want to gain a few electrons and fill their outer shell. FON, fluorine, oxygen, nitrogen. They are the most electronegative elements on the periodic table, and they're bonded to hydrogen, which is a small atom with just one proton in the nucleus and one electron. So there's not a whole lot of attractive force coming from the nucleus to hold on to that electron. These are like as close to ionic as you can get, while still sharing the electrons and not completely transferring. There will be a very large difference in electronegativities, but yet we still share. We are not quite transferring the electron. So, here's your choices. It could be H2O, water. Very, very common hydrogen bonder. It could be HF, or it could be NH3. Those are your options, I'll tell you right there. Hydrogen bonded to fluorine, oxygen, or nitrogen. And that's what their formulas would look like. But in concept, like in theory, it's the same as a dipole force. Look at a water molecule. So you draw a water molecule. Let's say do the Lewis structure. 2, 3, 4, 5, 6. We have the hydrogens. 1. We have the hydrogen 2. Here we go. That's what we mentioned earlier, that this is a polar molecule. It's a bent molecule. So I actually kind of drew it angular. If you're drawing as like a space filling or kind of like a ball and stick model, you can kind of see that like this is angular, that this is like a bent structure. And then you'd have your lone pairs kind of sitting up on top of the oxygen. So the red atom is the oxygen and the white ones are the hydrogens. So number one, this is a polar molecule. The oxygen end is slightly negative and the little hydrogens are slightly positive. Because there's 4 stinking electrons sitting up on top of the oxygen, electrons are negative. Plus, these are such polar bonds. Oxygen has a really high electronegativity. So the electrons in these bonds are also drawn toward the oxygen. So there is no doubt in my mind that the oxygen end of the water molecule is slightly negative. The hydrogen end is slightly positive. So when you have a whole bunch of these molecules that are all kind of next to each other, check it out. The slightly negative oxygen end is attracted to the slightly positive hydrogen end. Hydrogen attracted to oxygen. And this happens throughout the entire sample. Now these are called hydrogen bonds. And I hate the word bond. I cringe calling them bonds. To me, a bond is ionic or covalent. A bond either transfers or shares electrons. Well, I wish this was called like a hydrogen force or something like that. It's an intermolecular force. It is between the molecules. So if you tell me that you're breaking hydrogen bonds, I will assume that you mean that you are changing phase. Breaking hydrogen bonds involves separating the water molecules. And that would be a physical phase change. Let's say I have water in the liquid phase, and I'm overcoming this hydrogen bond. I'm separating the molecules, but I am not breaking these guys. These I would call covalent bonds. Or to be more specific, I could call them polar covalent bonds. If you break that bond, now that's the chemical reaction where you'd form hydrogen gas and oxygen gas. A common test question will ask, what is the identity of the gas in bubbles of boiling water? If the water is just boiling, we're just breaking the hydrogen bonds between the molecules, and so the gas is just water in the vapor phase. It's still H2O. We're just overcoming these attractive forces between the molecules. The wrong answer would be some form of like hydrogen or oxygen gas. Now, hydrogen and oxygen gas, that would be a chemical change, not involved in boiling. If you took like a lit wood splint and hold it over a sample of boiling water, it just goes out because the gas is just water vapor. If you hold a wood splint over hydrogen or oxygen gas, well, hydrogen is flammable. It should pop. Remember when we did that test a while ago? We'd like pop the hydrogen in the test tube. We burned hydrogen in like bubbles of hydrogen. And oxygen also supports combustion, so like your flame should get real bright. That shouldn't happen above boiling water. So the concept of a hydrogen bond is the same as a dipole force. It's an attractive force between polar molecules. These hydrogen bonds are just a little bit stronger because it's a more extreme dipole. You're dealing with little baby hydrogen and the three most electronegative elements on the whole periodic table. So these guys should have a little bit higher melting and boiling points as opposed to a substance where the intermolecular force is a dipole force. They're just a little bit weaker because the electronegativities are a little bit closer to each other. If you're ever answering a question about water and you're having a brain freeze, just start talking about hydrogen bonds. Water has a pretty high boiling point, as opposed to other liquids. Like alcohols might boil in the 70s. Water's boiling point is 100 degrees Celsius. It's because of the attractive forces between the water molecules. It's because of hydrogen bonding. These water molecules are very attracted to each other. It's going to take a lot of energy to separate them. Water has a high heat capacity. It takes a lot of energy before you can change phase. Because again, the particles are highly attracted to each other. Or you could have like a pool of water and a concrete surface surrounding the pool. And you put your foot in the water and it's cold. While the concrete surface is really warm. They've been under the same sun for the same amount of time. But it takes more energy to start increasing the temperature of the water, to start making the water molecules move around faster. They have a high heat capacity. They're highly attracted to each other. Water has capillary action, high capillary action. Like if you suck water up a straw, and all the water molecules come up the straw. Or a high surface tension where little bugs and leaves can kind of float on water because the liquid molecules are highly attracted to each other. So if you're talking about water and there's a question that pops up and you really seriously have like a brain freeze, start talking about hydrogen bonds. It'll probably lead you in the right direction. There's one other attractive force that we should mention, and that deals with ionic compounds. Ionic compounds have the all-time highest attractive force between particles. Because now we're not just talking partial positive, partial negative. We are talking attraction of oppositely charged ions. This is a full out +1, -1, transfer of electrons. These attractive forces are stronger than something that's just partially positive or partially negative. And so when we think about like the structure of an ionic compound, we kind of mentioned this back when we were doing bonding. They're real crystalline. Ionic compounds have a very organized crystal structure of repeating positive and negative ions. They're in this crystal lattice. Like if I just pinpoint one little ion, so let's say here's kind of this positive sodium ion, it is completely surrounded by negative chlorines. Chlorine, 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 chlorine. And then what do I have next door? I got a bunch of sodium, sodium. There's more sodium surrounding all the chlorines. And it's just a repeating pattern of oppositely charged ions that are all very attracted to each other. And these are stronger yet than any partial positive or partial negative. Back in the day, we were trying to change phase. For ionic and covalent compounds, we were heating them. We're seeing like which one had the highest melting points, and we by far found that the ionics had really high melting points. Even like with a direct flame from a Bunsen burner, we couldn't melt an ionic sample. The attractive forces between the ions are just too strong. Really high boiling points or melting points, because these intermolecular attractive forces are the strongest. So when we start looking at comparing boiling and melting or any kind of phase change, it's all about comparing the intermolecular attractive forces. The stronger those attractive forces between the particles, the more energy required to change the phase.